Hi everyone, my name is Chung-Yi. I will be your TA for the class CEE122, and this video is for the very first recitation for this course. So I will go through the homework solutions for the week 1. So let's start. The first question, the first problem, 2.12. We want to find the dynamic and kinematic viscosity for the kerosene and the motor oil and water at temperature of 50 degrees Celsius. So let's label this item to be 1, this as the motor oil to be 2, and the water to be 3. Okay, and we also denote the dynamic viscosity as this mu, and kinematic viscosity as this symbol. Okay, so that's right down here. 1, 2, 3, mu, tau, mu, tau, mu, tau. Okay, so to find the viscosity value for these 3 different items, we will need to utilize the figures and table in the appendix. So for the kerosene and the motor oil, we will apply the figure 8.2 at the page 9 in the appendix. Okay, so I already drew the reference line in this on top of this figure. I just want to show you the process of how to find those values. And this first figure is for the absolute viscosity, which is the dynamic viscosity. Okay, so for the kerosene oil, we first find the corresponding curve for this item, which is here. Okay, and we draw the vertical line as the 50 degrees Celsius temperature. So this line here, and then we find the cross sections with the item's curve and draw the horizontal line down, and we can find the absolute viscosity, which is the dynamic viscosity, by reading the number here. And for this question, I will use the SI unit, so that just read the value at the right hand side. And in this case, the kerosene will have the value equal to 1 times 10 to the power of 3. So it's not that close, but it is close enough. So let's just use this value for in this case. And similarly, we can use the same figure to find the dynamic viscosity for the motor oil, and the curve is here, and then you draw the horizontal line down, and value is around 4 times 10 to the power of 2 minus 2. So this is 1 times 10 to 4 times 10 to the power of minus 2. Okay, and for the kinematic viscosity, we follow a similar procedure, but using the different figure. So this is the figure at the page 10 in the appendix, and this is for the kinematic viscosity. So you basically do the same thing for the kerosene and this motor oil. You draw the vertical line down first, find the cross section, and then draw the horizontal line, and then you can read the corresponding value on the right hand side for the SI unit. And here I will just give you the value here, So for kerosene, the kinematic viscosity is 1.5 times 10 to the power of minus 6, and for the oil, the motor oil, is 4.5 times 10 to the minus 5. And unit, the unit for the dynamic viscosity is N times H divided by meters squared, and for the dynamic viscosity, the kinematic viscosity, the unit is square meter divided by second. Okay, and so now we have the value for these first two items, and for water we will utilize the table 8.5 at page 14 in the appendix. And similarly, for the first column is temperature, so we find the corresponding rule for the 50 degrees Celsius. Then we can read the dynamic and kinematic viscosity for the water, which is 5.47 times 10 to the power of minus 4 and 5.53 times 10 to the power of minus 7 for the kinematic viscosity. Okay, so let's write it down. This is 5.47 times 10 to the power of minus 4. This is 5.53 times 10 to the power of minus 7. Okay, so basically, if you know how to read those tables and figures, then you are good for this problem. So now let's move on to the next one. The problem 2.23. So we want to calculate the pressure increase that must be applied to liquid water to reduce its volume by 3%. So how do we do this? The equation that we're going to use for this problem is called the modulus of elasticity equation. And I will write down the equation for you here. The E is the elasticity, is equal to minus delta P times the volume divided by the delta volume, which is the change in volume. And we already know that the ingredients, the item is water, so we can know the corresponding elasticity for the water from the previous table that we used in the problem 1. So here is (2.2 GP), and let me copy that constant here. The elasticity for the water is equal to 2.2 GP kappa pa, which is 10 to the power of 9 pa. Okay, so the unknown that we want to solve is this delta P, and we want to know the delta P to reduce its volume by 3%. Okay, so we can plug in the number now. This elasticity is 2.2 times 10 to the power of 9, and this is the unknown that we want to solve, and this is the original volume, and the delta volume is we want to reduce its volume by 3%, so we want to reduce, which is minus 0.03, which is 3% of the original volume, and we can cancel this volume variable. Then the delta P is our only unknown here, so we can reorganize this equation. We can guess that delta P is equal to, cancel this minus sign out, 2.2 times 10 to the power of 9. Move this 0.03 from the right hand side to the left hand side, so times 0.03. Then we can get the volume 6.6 times 10 to the power of 7. And we can do some unit conversions, that this is also equal to 66 megapascal. And that is the pressure increase that we need for this problem. Okay, so basically you will need to know this modulus of elasticity equation to be able to solve this question. Okay, so let's move on to the next one. The problem 2.27 is definition questions. So the non-slip condition means the velocity v is the velocity of the wall. So you should be able, you should have learned this in the class or from the textbook. Here, it's basically mean this is the wall at the velocity v, and the point at here should have the same velocity to the wall. Okay, so that is the definition for the non-slip condition. And now we are good to move on to the next problem. The problem 2.32. The velocity distribution for water at 20 degrees Celsius near a wall is given by these equations, and the variable a and b is also given, and y is the distance from the wall in millimeter, and we want to determine the shear stress in the water at y equal to 1 millimeter. Okay, so we want to find the shear stress, and the equation for the shear stress is that the shear stress is equal to the viscosity times what? Du divided by dy. Okay, that is the shear stress equation. And for the viscosity mu here, we can use the table 8.5 to find the viscosity for the water at 20 degrees Celsius. And here I will just give you this constant value that the mu is equal to 1 times 10 to the power of minus 3 with the SI units. And for this term, because we already have the equation for the velocity u, so we just need to differentiate it with dy. So let's separate that term, and here is equal to a times this. And I hope you will know how to do the differentiation. And here I will just write it down. A is a constant, so we move out, and b is also a constant, so we can also move it out. 6. This is b. And we differentiate this y to the power of 1 over 6. We take the 1 over 6 out, move down, and then we times y to the power of minus 1, right? So we can reorganize this equation, and we will get the new equation that is equal to a over 6b times b over y to the power of 5/6. Okay, so we can plug this equation into here. So we have the shear stress equal to mu times A6b times b divided by y over 6. And because we want to find the shear stress at y equal to 1 millimeter, so now we can start to plug in the volume. This is for the viscosity is 1 times 10 to the minus 3 times A is 10 meter per square divided by 6 times B, and B is 2 millimeter, but we want to use the units of meter, so it's equal to 0.002 meter. Okay, because A have the units in meter per square per second. Okay, and we times the B is 2 millimeter and the y is at 1 millimeter to the power of 5/6, and this is the same unit. We can cancel it out and we can use a calculator to calculate the number, and we will get that the shear stress at y equal to 1 millimeter is equal to 1.485 Pa. Okay, so basically for this question you will need to know the equation for the shear stress as I show here and know how to do the differentiation, then you should be good for this problem. Okay, so let's move on to the next one, which is the last questions that we have for the homework 1. The problem 2.37, we have a sliding plate viscometer shown below is used to measure the viscosity of the fluid. The top plate is moving to the right with a constant velocity of v equal to 22 meter per second in response to a force of F equal to 1 N. And the bottom plate is stationary, which is the velocity equal to 0. And what is the viscosity for fluids? That is the main question and we want to solve for this problem. So let's back to the definition of the shear stress, shear force. The shear stress is equal to the force divided by area, and it's also equal to the viscosity times dV divided by dy. Okay, so we will use this relationship to solve the viscosity. So that means we will need to know the viscosity is equal to the force divided by area times 1 over dV dy. Okay, and we know the force is equal to 1 Newton. So this is 1. And the area is equal to 100 millimeter times 50 millimeter, but we want to use the unit in meter, so that means we have 0.1 meter for this one, and this is 0.05 meter. Okay, so the area is 0.1 times 0.05, and this is 0.005 meter square. So we also have the area here, 0.05, and then because we assume a linear velocity distribution, so it's basically the slope of the velocity. So this dv over dy is the delta v divided by delta y is 22, because we have the top plate moving as 22 and the bottom plate have the velocity equal to 0. So the difference is 22 over the gap between these two plates is 1 millimeter. That is 0.001 meter. Okay, so we have divided 0.001. Okay, so this gives us 2. Okay, and then we can plug these into this equation. Then we can get the value for the viscosity. That is equal to 9.09 times 10 to the power of minus 3, with the standard SI units for viscosity, the Newton times second divided by square meter. Okay. So just a quick overview for this last problem that we have. The equation that you need to know in order to solve this viscosity is the relationship between two different equations for the shear stress. So the basic definition for the shear stress is the force divided by the area, and we also know the equation that is equal to this viscosity times the dv over dy. So with these two equations that can describe the shear stress, we can reorganize it and we can isolate the viscosity out from these two equations. And for rest of the variable is already given in the problem, you just need to plug in all those values back into the equation and you can get this the value for the viscosity. Okay, so that is the last problem we have for the homework. And just a quick heads up for the quiz that we will have during our in-person recitation. So the quiz will be one question that is similar to one of the problem that we have in this homework. Maybe I will change some number in the problem or just a simple modification from one of these problems. Okay, but just keep in mind that this quiz is closed book, so you cannot bring the equation sheets to this quiz. The only thing that you can bring is your calculator and the pen. And remember that you cannot use smartphone as a calculator. You have to bring your own really simple calculator for the quiz. And you have to remember the basic equation like the definition for the shear stress or the module of elasticity equation. But for the constants like this elasticity for the water, if it is needed, I will provide you those constants, but I will not provide you those equations to calculate for the answer. So just keep in mind that you have to remember all those basic equations in order to solve the problem the quiz, I mean. So see you in the in-person recitation next week. Bye.